We want to prove the implicit function theorem. I'm only going to prove the simplest case for a relation of two variables, or from which we extract a function of one variable. So this is the easiest case. And what I want you to do as we go along the proof is try to compare it to the example we did a couple of clips ago, when we discussed the example with y to the power 5 plus y to the power 3, or whatever that was, because the idea is kind of similar. Okay, the idea, it's different, but the idea is very similar. So I want to prove this. So let's do that. So this is the proof. I'm going to give the broad idea of the proof without being too careful about epsilon neighborhoods and so on. Just the idea. So otherwise the details get in the way of the important broader picture. So I'll write idea of proof. So one of our assumptions tells us that the derivative with respect to y at the point x0, y0 is not 0. That's an important assumption. That's what tells us that at that point we can proceed. Okay? So since this holds, we can assume without loss of generality, does everybody know this abbreviation? Without loss of generality, it's either positive or negative, right? So let's assume it's positive. df to dy at that point is positive. If it's negative, you run along the entire proof, the same arguments, just replace the sign. Okay. Now, since f is in C1, what does it mean that a function is in C1? It means that the partial derivatives don't only exist, but they're also continuous, right? So this thing, the df to dy, is a function of two variables, x and y. Since it's positive at some point and it's continuous, tell me if you agree to what I'm saying now. If a function is continuous and positive at some point, it's going to be positive in a neighborhood of that point. It can't suddenly be negative. Okay? It's continuous. If it's going to be negative, it's going to be negative a bit further away. Do you agree? So since f is in C1, df to dy is continuous, and therefore, and so, df to dy is positive, not just at the point, but at a neighborhood of x0, y0. Do you agree? Everybody? Okay. Now, let's fix temporarily x0. So for a given x0, again, df to dy is a function of two variables. I know it's positive in some neighborhood. Fix an x0, an x0, or no. Sorry, x0 is given. Sorry, erase that line. Sorry. So df to dy is positive. What can you say? What does this imply regarding f at x0, y? If I only look along the slice where x0 is fixed and I allow y to vary. So can you imagine, here's the graph, I'm fixing an x0 and looking only along this slice, I'm getting a single variable function in the variable y. Does everybody see that? And what do I know about this function? Its derivative with respect to y is always positive. Right? So what does it tell you about this function? This is a function of y alone, x0 is fixed. And its derivative with respect to y is positive. Right. This is an increasing function in terms of y. Does everybody agree? fxy is strictly increasing increasing in this neighborhood, when you're near y0. Clear? Okay, do you see the resemblance to the sort of arguments that showed up in that example that we did with the y to the power 5? Okay, we argue that the function is increasing. What does it mean that a function is increasing? So we can deduce from here that there exists a value y1 such that f at x0 y1 is positive, and there exists a y2 such that the value of f at x0 y2 is negative. How do I know this? How do I know this? Because I know the value of f at x0 y0. Maybe let's add it here. F at x0 y0, what's this value? This is 0. That's the second assumption of the theorem, right? The theorem had two assumptions, that this is 0 and that the derivative is non-zero. Remember? Look back at this board a second. Good? So this function is a function of y alone, is an increasing function. It's 0 at this point, at y0. So for some y greater than y0, it's going to be positive, and for some y smaller than y0, it's going to be negative. Do you agree? x0 fixed all along. Does everybody agree? Okay. Now, f itself was c1, so in particular f is continuous, right? In particular f is continuous, and why is that true? Why is a c1 function continuous? Remember, c1 implies continuous partial derivatives. Tan, 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 tan. Exactly, very good. So remember we had this block diagram where having continuous partial derivatives implies being differentiable, implies being continuous. Remember that? Okay, so f itself is continuous. Therefore, if it's positive at this point, it's going to be positive in some neighborhood of that point. And if it's negative at this point, f itself, it's going to be negative in some neighborhood of this point. Clear? So let's write that. F is continuous. F is in C1. And therefore, f is continuous. So, for any x near x0, f at x with that y1 is going to be positive, and f at x with that y2 is going to be negative. At x0 it's positive, it's continuous, so near x0 it's going to be positive. Note that I just released the first variable, which was a fixed x0 before. Okay? So now I fixed this one, made arguments about the y variable, and now these are fixed, and I'm releasing x and x0 and looking at x's nearby. Okay? Clear? So now I know that it's positive here, negative here, and this is for any x in the neighborhood. Okay? I'm doing this because it's only x is varying now. Okay, so for such an x near x0, for such an x near x0, what do I have? I have the value of the function. Now take an x near x0, a specific x. The value of the function at x, when you take y1 for the y, you get positive. For the same x, when you take y2, you get negative, right? What can you say? It's continuous. What can you say? At that x, it's gonna somewhere, for some y, it's gonna cross the axis. Do you agree? So for such an x near x0, since the derivative of f with respect to y is positive, that's true in the entire neighborhood, fxy is increasing, right? Since it's positive, it's increasing as a function of y. As a function of y. But now I'm looking at some x like this. The derivative with respect to y is positive, so it's an increasing function of y. It's negative here, it's positive here, so it's going to have a root, and it's going to have a unique root, right? So therefore, there exists a y somewhere between y1 and y2. And do you know this notation? This means there exists a unique y. Okay, that's this notation, but I'll write it in words. There exists a unique y such that f at x, y is precisely 0. So what did I just show? I took an x near x0, I found a unique y such that f of xy is 0, right? I took an x, I found a y, a unique y. I'm saying it again. I took an x, I found a y. What is that? That's a function. Okay, so we just found implicit. I don't have a formula, but given an x, there is a unique y such that if you plug in that y, you get 0. Okay, so this proves existence, or this proves that y equals some function of x exists. Okay? Do you agree? Good? And in fact, it proves exists and is unique, right? We claim that there is a unique implicit function. And it's unique. We found for every x, there's a unique y which would satisfy this. So there's only one way to prescribe y as a function of x. Okay? Clear? Do you see that this runs along the same line of arguments, only abstractly, of that y to the 5 polynomial that we had in the example a couple of lectures ago? Do you remember that? Everybody? Okay. So are we done? Can I put the square Helmholtz here? No. What do we still need to prove? Right. We need to prove the formula for the derivative. Okay. But in fact, that's rather easy. So, so this proves that y exists and is unique. Proof of the formula for f prime of x. So we know already, because we just proved it, that we can write y as a function of x. And it would satisfy that f of x equals 0. F of x, when I say this it sounds weird. F of x, comma, little f of x equals 0. When you replace y with f of x, it solves it, right? That's the meaning of being an implicit function of this relation, right? Okay. Let's take this and apply the chain rule. Okay, I'm going to apply the chain rule to this. So, by the chain rule, what do I get? The derivative of, I want to take the derivative with respect to the variable x. Okay, now there's a little abuse of notation here, because x is the first variable of this, but it's also the variable of little f. So you have to be very careful. So what's the statement? So the derivative of f with respect to its first variable, x, times the inner derivative. What's the inner derivative? 1, because the first variable is just x. So times 1 plus the derivative of f with respect to its second variable, df to dy, times the inner derivative here. What's the inner derivative here? It's just the derivative of little f, right? The derivative of y with respect to x. Do you agree? That's the chain rule. And that has to equal the derivative of this with respect to x, but the derivative of 0 is just 0. Do you agree? Good? Therefore, I can solve this for f prime. F prime of x equals, move this to the other side, minus df to dx, and divided by this, which is not 0 by our assumption. That's the proof of the formula.
Why does that equal 0?
I just took the derivative of both sides of this. Good? Okay. Now there's an interesting thing here. There are some delicate remarks which can be said. I don't want to confuse you too much. But there is something I do want to say. So this completes the proof. Now we proved the entire theorem. But I want to just remark one small thing. Doing this holds whenever there is a function, whenever a little f of x exists. And this is going to be true whether f of x, whether I found it using the theorem, or whether I found it by any other means. Okay, I can do this once I know it exists, right? I can do the chain rule. Do you agree? So even if you found little f of x explicitly, for example, or in any other way, this formula would hold. This formula, so this part of the proof does not say only if you found little f of x using these arguments that we had before, then this thing applies. No. If you have f of x, you can write this and then do the chain rule. That's it. Good? Clear? Okay, there's a little, you have to pay attention. So if, for example, you have to assume, if you want to do what I just said, you have to make sure that you're looking at f which is C1 and little f which is differentiable, because if you just find an explicit function, maybe it's not differentiable. The theorem guarantees that it's differentiable. Okay, but maybe finding it like this doesn't. So you have to be more careful in general, and then you'd be doing nonsense with the theorem. For example, this could be non-zero and this could be 0, and then you get nonsense. Okay, so but it's just because the chain rule won't hold if everything is not differentiable. Okay, so you have to be careful if you want to do what I just said in general, but for the theorem it's good. Good, everybody? Okay. So I know that this theorem sometimes scares people, and sometimes they say, whoa, this is so theoretic, although we did do very concrete examples, okay? But it's important. This theorem is so useful, and we're going to use it a lot in various cases, in various applications through the theory that we go through. So that's why it's worth the time we're spending on it, okay? And so having said all that, I hope you're not too scared, but we're not done with it yet. Okay? So I want to show you how to generalize this theorem for systems of equations. Not just fxy equals 0, but a bunch of them. Okay? And in addition, that I'm going to do separately, I want to show you how this theorem applies something that we said previously but never proved. Okay? Remember that we said that when you have I'm taking you way back. Remember that we said, when we discussed the gradient, okay, that the gradient of a function of two variables is always perpendicular to the level curves. Remember we said that? And the argument was pretty straightforward. Remember that? Everybody remember that? It followed from the formula for the directional derivatives. Okay? But we also said, okay, let's take this one step up. The gradient is perpendicular to level surfaces of functions of three variables. We never proved that. Okay? And the proof is going to follow from the implicit function theorem. And also more things are going to follow from the implicit function theorems, but that's why we're not done. But we're done for now. Okay, so let's have